Hello everyone, my name is Mr. John Mahlangu. I'm a lecturer at the Nkangala TVET College, Middelburg campus. I'm lecturing electrical theologies and mathematics. Today I'll be giving a lesson about ECDE Level 2. ECDE Level 2 is divided into 4 main topics: components and circuit drawings, digital electronics, computer components, transducers used in a process control. Each topic consists of subject outcomes. Our lesson for today will be from topic 1. Topic 1, components and circuit diagrams. Semiconductors on Module 3, Unit 3.1, Semiconductors Physics, and Module 4, PN Junctions. On completion of our module, you will be able to understand what is a semiconductor and distinguish between an intrinsic and extrinsic semiconductor. You will be able to explain N-type and P-type semiconductors using an atomic structure. You will be able to explain the meaning of majority and minority charge carrier. You will also be able to understand PN junctions. For starters, grab your books, grab your pen, and we are about to start. Semiconductors. What are semiconductors? We use them every day. Semiconductors are semi-metal materials that are neither a conductor or an insulator. Materials such as silicon and germanium. The material silicon that is used, the reason why they use silicon, it's simply because it's a type of material that can sustain heat. Silicon, it is simply used because it's a type of material that can sustain heat. Semiconductors are used in manufacturing of electronic devices such as transistors, computers, radio. They play a huge role in today's modern electronics. Just like any other electronic devices, semiconductors has got properties. Properties of a semiconductor. The resistivity of a semiconductor is less than that of an insulator, but more than that of a conductor. Semiconductors have a negative temperature coefficient of a resistance. That means the resistance of a semiconductor decreases with an increase in temperature. This means that when the temperature goes up, there is a change in conductivity of a semiconductor, meaning that when the temperature goes up, the conductivity of the material also goes up. When a suitable metallic impurity, such as arsenic, gallium, is added to a semiconductor, its current conducting properties change considerably. We will learn more about metallic impurities as we proceed. Semiconductors are of two types: intrinsic semiconductor and extrinsic semiconductor. If you understand fully what is an intrinsic semiconductor and what is an extrinsic semiconductor, you'll be able to manage to understand the whole module 3 of semiconductors. You will be able to answer certain questions in future. Let's start with intrinsic semiconductor. An intrinsic semiconductor is a semiconductor when in its pure form, just like what? Germanium and silicon are a perfect example of an intrinsic semiconductor. This, what I'm going to draw now, it's an this here, it's a germanium. This, it's a germanium. I will explain it into details in order for you at home to understand. Remember what we said. We said that intrinsic semiconductor is when a semiconductor is in pure form. In this case, a germanium is a semiconductor. When you have this type of crystal structure of a germanium, we consider it to be in what? In pure form. We consider it to be in pure form. On your TV right now, you are seeing a two-dimensional representative of a germanium crystal structure. In order for us to understand an intrinsic semiconductor further, if you can look at this structure here, you see a GE. This stands for a germanium atom. In this case, when you build an intrinsic semiconductor, valence electrons are shared around the crystal. If you can see, these ones are what? Are valence electrons. When valence electrons are shared, they form a bond. This bond. They form a bond. This bond. When they form a bond, this bond is called covalent bonding. This bond are called covalent bonding. The covalent bonding are demonstrated by a dotted line. If you can make reference into our textbook, this textbook, Electronic Control and Digital Electronics, you will understand it much better. Even on our slide, it is being demonstrated that covalent bonds are demonstrated by what? By a dotted line around what? Around the valence electrons. Going forward, at a low temperature, all valence electrons are tightly held by a covalent bond. And this means that the valence electrons cannot move in the crystal. They cannot move or do anything in the crystal. In that way, this germanium atom cannot conduct electricity. Remember, in order for the conduction of electricity, you need a movement of electrons. In this case, we are at a low temperature. At a low temperature. Everything that I explained falls under low temperature. Now, going back to our slides, if the temperature is increased to room temperature, some of the covalent bonds are broken. Let's look back on our crystal structure. What they are saying when they say when the temperature increases to a room temperature, some of the covalent bonds are broken. What they mean is that this covalent bond is broken, and when this covalent bond is broken, valence electrons start to move from one covalent bond to another. These valence electrons start to move from one bond to another. When they move like this, they leave behind a vacant. They leave behind a vacant space. If you increase the temperature, you'll get a high movement of valence electrons, and at some stage, you will find a vacant space here. A vacant space after the valence electrons has moved, we call it a hole. A hole. That's what it is left when the valence electrons have moved from one bond to another at a high temperature. At a high temperature. Going back to our slide, to further understand what happens if the temperature it is high. The result in the electrons leaving its original position, and these electrons is now free to move everywhere within the crystal. The resulting vacancy of an incomplete covalent bond left behind by the dislodged electron is called a hole, as I have specified, indicating the absence of a negative charge. A hole can serve as a carrier of electricity like free electrons. A combination of such free electrons and a hole is known as electron-hole pair. If the temperature is increased, a large number of electron-hole pair is generated. Now that we are done with intrinsic semiconductor, we are entering extrinsic semiconductor. Extrinsic semiconductor. They are valence. Let's put this back. These ones are covalent bonds. I put them back because we'll still talk more about them. Back to extrinsic semiconductor. Extrinsic semiconductor, the result after the process of adding impure atoms to intrinsic semiconductor. At room temperature, the conductivity of an intrinsic semiconductor is very low. We need to add an external amount of impurity atoms to make it extrinsic semiconductor. The process of adding impurity atoms is called doping, and the added impurity are called dopant. I will demonstrate further after this slide on how do you add more impurity atoms into an intrinsic semiconductor. The main purpose of adding impurity atom is to increase the number of holes and to also increase the number of free electrons. Impurity atoms. I have told you that we will demonstrate on how to add the impurity atoms. Impurity atoms added to a semiconductor are either pentavalent impurity or trivalent impurity. Pentavalent impurity atom consists of 5 valence electrons. If you can remember, a germanium crystal has got what? Has got 4 valence electrons around it. And if the temperature is increased, you still have another germanium here with exactly the number of valence electrons around it. This trend continues with an increase in temperature. I want to explain what are impurity atoms on my board. Impurity atoms are divided into a pentavalent and a trivalent impurity atoms. A pentavalent and a trivalent impurity atoms. Impurity atoms. If you can check, here is a pentavalent, here is a trivalent. A pentavalent impurity atoms are atoms with 5 valence electrons. A trivalent are impurities with 3 valence electrons. I hope you are able to see clearly there at home and you are taking down notes. In this case, in order for us to find an extrinsic semiconductor, you need to add a number of impure atoms into an extrinsic semiconductor to make it an intrinsic semiconductor or to make it impure. Let's take, for instance, an aluminium. An aluminium has got 5 valence electrons. When you add an aluminium on a germanium, remember a germanium has got 4 valence electrons. It is pure because it is a complete atom with 4 valence electrons. When you add an aluminium into a germanium, this is what's going to happen. Over the 5 valence electrons, 1 valence electrons will be added here, The other valence electron will be added here, the other one here, the other one here, and the last valence electron will be a free electrons out of the crystal. Again, when you take a trivalent impurity atom and add it on a germanium or a silicon, the number of valence electrons of a germanium and the silicons are equal. So in this case, when you take, for instance, a phosphorus has got 3 valence electrons. When you add a phosphorus onto a germanium, what you get is that since well it has got 3 valence electrons, 1 electrons will be added here, another one will be added here, another one will be added here. Since well there are 3, in this case you'll be left with a hole here. And remember, for us to obtain a covalent bond, you need a pair of what? Of valence electrons. To understand the impurities is that the pentavalent electrons results into having an extra free electrons, and a trivalent impurities results into having a hole. That's the difference between a pentavalent and a trivalent impurities atoms. Below are an element of a pentavalent and trivalent impurities. On element 1, we have a phosphorus, the one that we used here. A phosphorus, the one that we use here. We have an arsenic, we have an antimony, we have a bismuth. Under trivalent element, we have an aluminium. And aluminium is the one we made an example of here. The one we made an example here. And we also have a gallium, a boron, and indium. We have the N-type and the P-type semiconductor. The N-type semiconductor are semiconductors which are obtained by adding a pentavalent impurity atoms. Remember, the pentavalent impurity atoms, it is being achieved by having 5 valence electrons. So an N-type semiconductor is achieved by adding a pentavalent into what? A pentavalent impurity atoms. Another thing that we get under the N-type semiconductor is that by adding a pentavalent impurity atoms provides a high number of free electrons in the semiconductor crystal. Such impurities are called donor impurities. The reason why they are saying it is donor impurities, if you can look back on our germanium crystal, if you add a pentavalent impurity atom, you'll be left with a free electron. You'll be left with a free electron. With a free electron. This electron, if it finds a covalent bond that is short of a valence electron, it will be donated into a covalent bond. That's the reason why they are calling the N-type semiconductor the donor's impurity. The 5th electron, as I have explained, will be called a free electron. The electrons in the N-type are known to be the majority charge carrier and the holes to be the minority charge carrier. Another reason why they are saying that electrons are a majority charge carrier and holes are a minority is that if the temperature is increased, you will have more of free electrons. You will have a free electron here, you will have another free electron. So these electrons become more in a crystal. This means that this N-type semiconductor has got electrons as its majority charge carrier and holes as its minority charge carrier. Now let's focus on P-type semiconductor. Semiconductor which are obtained by adding a trivalent impurity atom. By adding a trivalent impurity atom provides a high number of holes and a less number of free electrons in a semiconductor crystal. Such impurities are called acceptor impurities. In this case, if you have added a trivalent impurity in your germanium, remember, you will have what? You'll be left with a hole. When having a hole here, a free electrons, when the temperature is high, it will be added onto a germanium crystalline where there is a hole. In this case, the donor donates into the hole, and this covalent bond becomes an acceptor impurity atom. That's the reason why they are calling them an acceptor impurity atoms. After adding a trivalent impurity atoms, only 3 covalent bonds will be created, which will result into a hole in the P-type being majority charge carrier and electrons as a minority charge carrier. On your slide, you can see a demonstration of an N-type and a P-type semiconductor. Let's say this is an N-type, this is an N-type, and this is a P-type. The black marker will represent holes. And the red marker will represent electrons. Let's quickly do it before we run out of time. So in this case, what I'm trying to demonstrate is that the P-type material will have less number of electrons but high number of holes, and the N-type material will have a high number of electrons and less number of holes. Our lesson will end thus far. Catch us on our social media platforms, on WhatsApp, on Facebook, and Twitter. And you can also email us for any question you have. Thank you and goodbye.